Okay, hello. In this video, I'll be introducing the concept of linear approximation or linearization. I have it all written out here nicely because my tablet stopped recording in the middle of my last video. So let's walk through this together. This should be a pretty familiar concept to you. It's something that we've seen before back when we were using rate of change to estimate future growth, like population growth, for example. So using the current value and the rate of change to predict what will happen in the future. All right, so the general function for linear approximation or linearization looks like this, where we have the rate of change here, f prime of a, the derivative at that point a, and being multiplied by x minus a, so the difference in the x values, plus the current value at that point a. So the linearization is dependent on the function f and on this value a at the point where you're creating the linear approximation. So it's best to just see this example. Here we have f of x is the square root of x, and let's look at the point a equals 4, because that's a nice point, right? I know how to take the square root of 4. That would just be 2. So the linear approximation at this, we need f of 4, which we have, and we also need f prime of 4. So we take the derivative f prime of x, and we evaluate it at that point at 4, and we get 1/4. We get that slope. So our linearization will be 1/4 times x minus 4, minus the a value, plus the actual value at that point, plus 2. One way to think about that is by considering this graph over here. We have square root of x, and we have this point 4, and that's where we take the linear approximation. It's basically just the tangent line at that point. The only thing that's different now is we're going to use it to approximate points that are nearby. So for example, if we tried to find the square root of 4.1, right, that's very close to 4, we can think about it as a point along this line, and it'll be an approximate value for the square root of 4.1. It's placed on this curve. If we took points that were farther away, like over here or way up here, it would start to be a very poor approximation. But close to a equals 4, it's a good approximation. So we plug that into our function, and we see that we get this rate of change, 1/4, times the difference between those values, right? We have x minus a here, plus our value f of 4, and we see that the approximation is 2 and 1/40. Which is a pretty good approximation for square root of 4.1. Definitely much better than something I could just guess, pull out of a hat. Okay, another way to think about this whole concept is this idea of differentials. It's very closely related to linear approximations. So the idea here is it's kind of just a different perspective. We can take the derivative of our function, think about it as dy dx, which we've seen before. But now what we haven't done before is we're going to try to take dx and sort of multiply it to the other side. Now that didn't make sense with what we did before because dy dx isn't a fraction. Dy dx is this operator, d dx, which means take the derivative with respect to x, being applied to this function y. With differentials, we're going to just sort of pretend that it is a fraction and move dx to the other side. So what this will do is we'll think of dx as being kind of representative of delta x, which is the rate of change of x, and dy as representing delta y, the rate of change of y. And so this is showing their relationship. As x changes, how does y change? So let's look back at that same example. In that example, x is, let's say, 4.01, and our a was 4. So that means our dx, how x has changed, is 0.01, right? We've changed a very small amount. Then what dy will be approximated as, is 1/2 square root x. Well, at this point, we're looking at this point 4, right? And then that's the rate of change at that point. And then times dx. Our dx, we've moved 0.01. So our dy, this will move 1 over 40. So basically what this means is that when we're looking at this value, the change from 4 was 0.01, right? That was about delta x, so we're going to call that dx. So the corresponding change from y equals 2 should be approximately dy. So that's why we can approximate the square root of 4.01 as the square root of 4 plus an extra 1 out of 40, right? So it's two different ways of looking at the same thing.